Okay, welcome back, everybody. So that was a morning really dedicated to understanding the relationship between virtual humans as potential digital twins and improving human performance. And one of the great programs that has the opportunity to impact the Army for the next generation of soldiers coming through. I now want to introduce Dr. Karim Malek, Director of the Iowa Technology Institute, just to provide more background on the digital twins as they apply not only to this specific work with the ACFT, but more broadly. So Karim, over to you.
Thank you, Travis. Can you see my screen okay?
Yes, good to go.
Great. I'm going to spend this next 20 minutes just explaining the story, the history of how we came up with Santos, what it is, what's inside it, and doing that with a focus on both the digital twin world, but human performance in specific. Most importantly, I'm going to focus on just being an integrated virtual human. It's not just the biomechanics. It's not just the looks of what Santos or Sophia or any avatar look like, but being integrated with physiology, biomechanics, all of it together. 2 is the physics of the human and the environment. And then 3, assessing the human performance metrics and how we do this. Let me start by saying it's been 15 years, 16 years now. So Santos is about 16 years old, Sophia about 14. And, you know, both models made of about 215 degrees of freedom. We call the elbow 1 degree of freedom, the hand 25, and so total together 215. Santos is made up of skeleton, anatomy, muscles. He looks almost real. Obviously, you know, we're not focused on the looks of it. We would love to partner with others to do that. He has an entire muscular system that is able to sustain torques and stresses. In about 04, 05, we started the program with just the idea of how do you predict motion? How do you tell Santos, I want to move somewhere, but respect the environment, respect your ranges of motion. Here's the target, try to reach that. And in that process, we were able to do assessments of just posture, reach, vision, maybe some static forces, very simple things. What we were able to do then is this program was with Harley-Davidson up in Wisconsin, and they wanted a Santos model that they can vary a little bit to see how, for example, he would reach, what the posture looks like, why, you know, riding for long term would induce stress at L4, L5 in the back, given a specific posture, and so on. Same things, even at, you know, then 04, 05, we were able to do very simple things. As you can see, lower robotic motions at that time, but we were able to do a little bit more of vision, a cone and acuity of the vision, some collision detection, reach issues. Can you maintain this? Can you reach that? Slowly, and it took us really about 8 years to do something that we call now predictive dynamics. And so, as you know, given the human body, it's like just a robot of many, many degrees of freedom. The equations of motion, Newton's laws apply. And so you have to solve that in order to arrive at a solution. So how do you do this? Most people try to integrate these equations, and that's incredibly difficult. It's actually impossible, just incredibly computationally intensive. And so we took a different route. We looked at using optimization to do this, where we drive the motion and the behavior of the model using optimization and cost functions. So we say, for example, hey, Santos, now you're going to ride a ride and try to reduce your energy subject to all the motion around you, the physical laws of motion, the target that you want to reach to, the constraints, and try to do that motion. So in this case, we subjected him to a ride. And so the dynamics of the motion take over, the dynamics of the environment and the dynamics of the person start interacting. And what you get is a behavior of some sort that he will respond to. At the time, in terms of assessment, we were able to calculate now at this point, in 2014 or so, with this method called predictive dynamics, we're able to calculate torque, stresses, energy. Now we have energy. You can calculate hydration levels. You can calculate fatigue levels. And so it started, honestly, in about 2014. It took us about 8 years, 9 years to come up with this formulation. But finally, aha moment, we have something that we're able to subject the model, whether it's Santos or Sophia, to do things that are real. You subject them to things and they come back and say, yes, I can do this. No, I cannot do this because of the physics, because of the load. Now, a lot of people say, well, the human body, if you put an avatar in an environment, in a game environment, you say, hey, carry this table's 300 pounds. Can you lift it up? An avatar does not understand the strength limits of a human body. And so what we've done is bring cohorts of people. So did the military, the Marines in specific, bought similar machines as we have. They're called Biodex machines. And they would measure strength at every major joint, not all joints in the body, but major joints in the body. And that would constitute the limit of what we can do. So if you say, hey, Santos, try to carry this huge box, and given your body type, your weight, your dimensions, and so on, anthropometry, to try to carry that box, Santos would go and try to do that. And he would generate a torque at his elbow, for example, that is substantial. And you have to compare it to something that we know of. And so that's where the limits of human strength come in. We've tabulated now for about 10 years, lots of data that is really the limit of what a person can do. Same thing for Sophia as well, and variations thereof. So with that, we're able to do now truly physical activities where you can change the body or you can change the environment. Here's a program that we've done for the medical command. It's actually Center for the Intrepid down in San Antonio. They receive a lot of veterans that have lost limbs, and they wanted us to create a way to exchange part of the limb, the lower prosthetic device. And so, as you know, the training, once somebody comes in, amputee gets a prosthetic device, is not an easy fit. It takes time to learn how to walk, the gait itself. So they've asked us to create this tool. And all I'm trying to demonstrate here is that because he's physics-based, because he's physiology-based, you are able to do this. You're able to remove part of his body and say, I'm going to change it now with a rigid body that has limited joints or a different, and he will respond. We don't teach him how to walk. He is able to walk and demonstrate how he would do that if that prosthetic was this long or that long or this, design or another. Carrying on now, we wanted to induce behavior, and so people do things different ways. If you're tired today, you will do a motion, you will perform a task, you will conduct your mission in a very different way than yesterday, where you were not tired, you were not stressed. And so using this optimization formulation that we've been working on for exactly 16 years now, I'm going to summarize it like this. The cost functions, the human performance functions that drive the motion for Santos and Sophia is made up of multiple things. In this case, I'm going to demonstrate with two just simple postures. One, I'm going to say, hey, Santos, minimize distance, try touch the sphere, and he just did that without looking at it. Now I want to induce different behavior. I'm going to say, do the same motion, but minimize distance and maximize your vision. Remember, vision is some sort of a cost function that says, I know where things are. There's a cone. It's a vision acuity. I know where my target is with respect to the cone. Maximize that. And so now he drives the motion, inducing a different behavior. And so that's the main concept. Now we're able to say, today, you're a 21-year-old female, this anthropometry, this body type, and you're exhausted. And so try to accomplish this in a different strategy. So we change the cost functions than what was yesterday when you were not fatigued, you were not, and so on. As they do this, we're able to assess things. stresses, everything in gray I've talked about, but now we're also able to assess behavior and strategy. Is it easy? Not really. Is it computationally efficient? Not quite there. Is it real time? Some of it is real time, some of it is not. So I keep telling people, yes, we've been working on it for 15, 16 years, but we're just scratching the surface. There's so much to be done, the cognitive aspect. And so what we're looking for, particularly in this summit, is just to collaborate with people that are experts in one area or another. I think we would benefit all together. We would benefit the military if we come together and exchange ideas and add capabilities to to provide solutions. As we went along over the past many years, we've worked a lot with the military and other entities to bring data in. In some cases, I'm just going to cover a few. For example, Usarium up in Natick, Massachusetts, has done incredible modeling work on metabolics, on heat transfer, thermodynamics, and so we've partnered with and got data and models to implement inside the Santos model, Santos and Sophia. Same thing with the Marines. Same thing with SPA War and so on. We just keep adding data. But the one key issue to remember here, it's an integrated human. It's not just about having one model represents thermodynamics, because thermodynamics, is connected to hydration, is connected to energy, metabolics, and how you move, the biomechanics. All of it is integrated and has to be modeled in that way. In terms of as a digital twin, trying to assess things, and so now we're able to do heart rate, fatigue, energy, heat transfer, hydration. We do that through creating the motion and then calculating what we need from it in terms of performance. So here's two examples. A Santos, that same Santos, so same height, same weight, same everything. One is trying to do a task, same task exactly, and they conduct these tasks. One is much more loaded than the other, and then as a result of this, we're able to calculate things like that. Is it 100% accurate? No, it is not. However, it's close. It gives the commander, the strength and conditioning coach, the designer, the procurement agent, the purchasing agent that is trying to assess a new piece of equipment, a great idea, not 100%, but a great idea, I would say in the 80% range now, of what are the results. Can you change things and do it again? Can you change the body type and do it again? Yes. And so talking about body types in the Santos Sophia environment, you are able to go in and change just about everything. But because of usability, in some cases, we limit that and we provide. So, you can certainly go in the Santos Pro version and say, hey, I want to change the leg length for this particular avatar, this digital twin, and make it longer. And so now you expect that all the performance that Sophia Santos will do will be completely different. However, working with the Marines, for example, they've asked us to, instead of having this ability to change everything, let's define the boundary of the population of the Marines. They've done a lot of work within the Army called the answer data. So we've worked with them to identify the 7 boundary of male, 7 boundary of the female, the tallest, strongest person, the tallest, not so strong. And these are the boundary. And we are able to pass those through very quickly in a loop to see what they will be able to do, how they do it, and assess things. So another program that we've worked on, and I just want to demonstrate soldier variability. So this is the McLeap system. It's the Marines 32, I believe, warfighting scenarios. Throw a grenade, go through, climb over a window, take prone, climb steep stairs, and so on. One of them is vertical jump. And so I've asked Sophia as a 60 kilogram to do this on this side just to see how the response is, and Sophia as a 51 kilogram person doing that as well. And as you can see, Yes, we record motion from motion capture. We bring people in, we record their motions, and then Santos, Sophia learn from that motion, but then you ask them to do things and they will do it according to what they can, what strength they can to do it according to their body type, their weight criteria, and so on. Same on the ground, same, just different tasks that they do and how Santos, Sophia can do the same thing. And while they're doing this, we're able to assess, in some cases, speed was a big issue. Can you accomplish the task within a certain time? Other questions are, can you accomplish the task? If somebody buys a new piece of equipment and it has all sorts of limitations on the range of motion, a new body armor, incredibly heavy armor, a new weapon system that needs to be assessed, but the weapon system is incredibly cumbersome, heavy, restraining for a very small female, the system, Sophia, will be able to talk back and say, I should qualify that, tell us back. They don't talk yet. They qualify back things and tell us, yes, I'm able to do this. That's my metrics. That's why I was not able to do that. Some of the programs that we're currently working on, we're just incredible honor and pleasure to be working with the Army Futures Command, specifically the Data Analysis Center, Ron Bowers, who I believe is on the call, as well as Greg Dietrich. It's just been a great partnership working on their system called the Overmatch. We provide a very small aspect of it to assess the soldier as new equipment come in. And so we're building with them this environment. And the idea is to bring systems in, a new weapon, for example, and say, hey, Santos, Sophia, change your body type, change your environment, change the task, and tell us what your mobility level is or index. What's your survivability? They have incredible power in the ORCA model that is able to assess injury, casualty assessment in general from explosions, from weapons, and so on. So we're trying to, Ron and Greg with their program, trying to tie a bunch of technologies together in order to serve the Army better. Finally, and I think you've heard already quite a bit about the work we're doing with the Army Combat Fitness Test. It's been a great experience for us learning about what the ACFT is about. Just incredibly well designed 6 events that really at the end of the day improve the readiness of the soldier. And so we've been at it for about 2 years now. And what we do is we bring soldiers in, ROTC in this cases. So we're on campus, we have access and great support by our ROTC folks. We bring the cadets in, they do the ACFT, they do common soldier tasks. We monitor them in a very scientific manner. We have motion capture systems. We bring them in, they do all these tasks, and then what we do is actually compare in a very scientific, rigorous manner a lot of the kinetic parameters, motion, torques, ground reaction forces, and now power as well, power calculations. What, for example, the power throw, how much power is needed to accomplish something versus also the common soldier tasks that are done on that side. So we compare the two in a rigorous scientific manner and to see the correlation between how can the ACFT, how does the ACFT improve and contribute to the common soldier tasks, therefore contributing to readiness in general. So this just shows the process of what we do. We bring people in, there's a lot of analysis involved, and then at the end of the day, comparison between the curves that produced by the ACFT versus the common soldier task. One last program, I'd like to just tell you that we've been involved. This is with the Marines, and it has to do with injury prediction. We call it malum. Malum means injury in Latin. So malum terminus means reducing or eliminating injury. For 3 years, we've gathered incredible amount of data, massive amount of data from 3 sports across 3 seasons, and we trained a system called the Santos malum system with all this data to predict injury. That was the idea. So, from player profile to body parameters, daily measures, previous injuries if somebody had, and here's the big. So once you train all of this, you have an AI system, an artificial intelligence system that is able to point at injury and say, on a daily basis, student Jones is about to get injured. We wanted to know if that green, amber, red target is getting close to saying, well, that person is about to have a musculoskeletal injury. And again, remember, this is massive data that's been trained into the system. Santos does the kinematics, biomechanics calculations in order to fill a lot of the missing parts. And here's the biggest finding that we found. Injury, especially musculoskeletal, take an ACL injury, was not based just because you had a previous one, but it was actually 3 specific reasons. So continuously, among all the injuries that we've noticed, the system pointed us to saying this person was injured because they had a significant stress, a significant lack of sleep. In fact, sleep came out as number one, all the time. And load means how much effort they've done across a temporal. So time was an aspect that we've tracked as well. How much sleep they got 2 days before, how much sleep they got 3 days before. And of course, this is involving a lot of wearables, a lot of questionnaires, a lot of that's a whole different discussion. But at the end of the day, what we were just amazed by is the notion that the reason for injury was not a previous injury. It's not because you made a little mistake here or a little that. It was much more a lack of stress, significant stress, a lack of sleep, and significant load over the past couple of days. Finally, what we're trying to do in the future, we're incredibly excited about porting a lot of Santos and Sophia code for the past many years that we've been developing into a professional, well-supported, as you all know, Epic Unreal Engine is just the Rolls Royce of the industry. And we're just incredibly happy to now start work on porting all of this into the Unreal, so it becomes much more widely available, easy to use, well supported. Very, very exciting for us. Finally, also as well, we're working with the university responsible folks to allow us to provide the Santos open source code. It is available today to the military, but we're working on also making it available to everyone who wants to collaborate, work with us. Thank you so much.
Thank you, Karim. For the sake of time, we have, I'll read back one question, and it's from one of our international observers or participants from the Indian Institute of Science in Bangalore, India. A question really getting at stability in Santos. What is the criteria for assessing and maintaining stability in Santos? So if you just have a minute or so to answer, I'd appreciate it.
Yeah, that's a great question. It's a very short answer. It's called ZMP. I believe it's called zero moment point. It's a method that calculates all the inertias of the body and then projects that. It's a well-known method. We didn't invent it. We use it. It's a well-known in robotics where a humanoid uses. That's what the method they use. It's called ZMP, zero moment point. And so you take all the torques of the body, you project that on the ground, and then there's a point that has to be within a polygon that's also projected on the ground. If the point is outside the polygon of those projections, then you're losing stability, and that's how we keep Santos stable.
Thank you, and I'm sure there'll be more conversations and discussions. And just for everyone to note, we have added a place on the submit your question, a place for you to enter your email in case we can't answer questions live. We can get back to you after the conference. And again, thank you to the international partners that are supporting, and we will be hosting that International Digital Human Modeling Conference in Iowa City at the University of Iowa next year at the same time, where we'll go much more in depth into the current state of digital human modeling. Again, thank you, Dr. Malek. Well, that was the first hour plus, and we really covered a lot of ground, had a lot of great material. This next hour coming up is going to be fascinating. It's the hour really dedicated to industry and our industry partners, those that are working to improve human performance through lots of different means. And it's interesting how the digital twin or the virtual human will begin working with these industry partners.